meant to record. All right, so we have a couple of things coming up. So we have our second quiz on Monday. So that's going to be March 1. So quiz 2, which is going to be on ANOVA and completely randomized block designs. That material or that quiz will be held in the same way as the first quiz. So we'll be doing it via CrowdMark. You'll be sent a link to the CrowdMark page before the exam. As a reminder, if you don't get the link, if you log on to the CrowdMark page and you refresh the page at the time the exam starts, then your exam will appear there. So that's usually the easiest way to get in and causes the least amount of stress. We also have the fourth assignment. I just need to check the due date for that. I believe it's March 5th, but I want to confirm that really quick. March 5th, yeah. Okay, so A4 is due March 5th. And, oh, it looks like lab assignment 3 is due March 1 as well. Oh, quiz, yeah, okay. Okay, so up until the break, we had covered a number of different topics. So we started off by reviewing sampling distributions, in particular the sampling distribution of the sample mean and the central limit theorem. In lecture set 2, we reviewed single sample hypothesis testing and single sample confidence interval construction. So we use both the standard normal curve and the student T curve to perform inference about a population mean via confidence intervals or hypothesis tests. In lecture set 3, we talked about two sample inference. So in that particular lecture set, we discussed confidence intervals and hypothesis tests for the difference between two means. In that situation, we only use student T values, but we differentiated between independent and dependent samples. And that was the material that was held on the first quiz and on assignment 2. Okay, so that's all material that we've studied up to and been evaluated on at this point. In lecture set 4, we studied one-way ANOVA. In lecture set 5, we studied residual analysis and multiple comparisons and contrasts following from the one-way ANOVA. And then in lecture set 6, we studied completely randomized block designs, and we also discussed the contrasts and the multiple comparisons that would follow from a completely randomized block design. Okay, so we have then, and then assignment 3, we had questions on the one-way ANOVA procedure and the multiple comparisons and the contrast. So assignment 3 covered that material. And then assignment 4 has completely randomized block design, which is lecture set 6, and the two-way ANOVA, which is the lecture set that we're currently working through. So at the time of the quiz, you would have been evaluated on the one-way ANOVA material, but you wouldn't have seen any questions related to the completely randomized block design portion. Okay, so lecture quiz 2 is going to be an amalgamation of lecture set 5 and 6. So it'll be the one-way ANOVA procedure mixed in with the completely randomized block design stuff. And in both cases, contrast and multiple comparisons would be something that falls out from that material. So a good way to get ready for the quiz is to use the practice problems that are posted on the course website. So there's some practice problems related to working through completely randomized block designs and working through the one-way ANOVA material. And also just to work on those CRBD questions from assignment 4, because that will also help you to prepare for the quiz on Monday. Okay, so today we're going to continue to work through lecture set 7, which is the lecture set that we started before the break. Does anyone have any questions at this point, just before I continue on with this material? Okay. All right. So we left off evaluating interaction diagrams. An interaction diagram is essentially a plot of the means for a particular experiment. Okay, so for example, when we have, well, let's start more closely to the beginning of the unit. So when we studied one-way ANOVA, we had one response variable and one explanatory variable. So we were interested in comparing the means of the response variable across the levels of the explanatory variable. In completely randomized block designs, we have the same goal, but we want to account for what is called a confounding variable. So we have a response variable, we have an explanatory variable, and we have a confounding variable. So we want to study a change in means across the levels of the explanatory variable while taking into consideration the blocking variable or the confounding variable. But we're not interested in studying the confounding variable directly. In two-way ANOVA, we have an experiment where we have one response variable and then we have two explanatory variables. So we want to study the impact of each explanatory variable, or we want to study a change in means across the levels of both explanatory variables. When we have two explanatory variables, we have to consider what is called interaction. Okay, so for example, in the illustration on slide 3, our response variable is the distance a golf ball is being hit by a machine. Okay, so the response variable is distance traveled by the ball. There are two explanatory variables: the golf ball brand, of which there are 4 types, A, B, C, and D, and the type of club you are hitting the ball with. So the driver versus the 5-iron. We can consider the levels of the golf ball brand and the levels of the club separately, and we can consider them together. When we consider them together, we create what is called interaction. So the interaction between the level of one explanatory value and the level of the other. So in this particular illustration, we actually have 8 treatment combinations, or 8 treatment combinations that result from the interaction of the golf ball brand and the golf club levels. We can visualize how a system is evolving by studying the means that result from these treatment combinations. So in the simplest situation, we would have two levels for each explanatory factor. So for example, on slide 10 here, we have explanatory variable 1, okay, and here we have explanatory variable 2. So we have 2 explanatory variables, and each variable has 2 levels. This creates a system of 4 treatment combinations. So 2 times 2 is 4. In this table, we have the means for each treatment combination. So the response variable here is tensile strength, which is measured in psi. So for example, the tensile strength of a siliceous static specimen is 68. The tensile strength of a basalt static specimen is 65. The tensile strength of a siliceous kneading specimen is 60, and the tensile strength of the basalt kneading method is 97. We can plot these means on what is called an interaction diagram. So an interaction diagram is a diagram where the y-axis is the response variable of interest. So in this case, tensile strength. And the x-axis is one of the two explanatory variables. So it could be either aggregate type or it could be compaction method in this particular example. Then what we do is we use a line type to designate the other explanatory variable. Okay, so for example, here we have aggregate type on the x-axis. So that was the first explanatory factor or explanatory factor A. And then we have line type representing the other explanatory factor. Each of these points is a mean. So for example, this point here is 68. That's the mean of the siliceous and static method. So the value from the table here, 68, right? For the static method at the basalt level, we have a mean of 65. Okay, so static basalt here is 65. Okay, so the interaction diagram is simply a diagram where we're plotting the averages for each of the treatment combinations. From the interaction diagram, we can work out whether or not there is the presence of the main effect, which is a difference in the average level of the two, is a difference in the averages when you compare the levels of each explanatory factor, and whether or not there's an interaction effect, which results from a specific treatment combination changing the direction of the system of means. So for example, here, the red dashes on the plot represent the difference in means between the basalt approach and between the basalt level and the siliceous level. So we can see that these two red dashes are at different points on the y-axis. This means that there is a main effect across the aggregate type. Okay. The blue dashes represent the average of factor B, which in this case would be the static versus kneading approach. So we can see here that the blue dashes are also at different value on the y-axis, which means that there's a main effect for B. Finally, the lines in the interaction diagram are not parallel to each other, which indicates an interaction. Typically, when the lines cross, we would consider that to be a strong interaction. When the lines do not cross but are not parallel, we would consider that to be a weaker interaction. So what we are doing is we are using the interaction diagrams to evaluate whether or not there is a difference in the average level across one explanatory variable and whether or not there is evidence of an interaction. And the purpose of this is to set up our two-way ANOVA analysis. So the two-way ANOVA analysis will will be very similar to what we saw when we studied one-way ANOVA. Or sorry, it will be very similar to how a one-way ANOVA or a CRBDF test unfolds. So basically, we'll construct an ANOVA table and we'll have a set of hypothesis tests that fall out of the ANOVA table. The interaction diagram is kind of like a pre-check of the system that allows us to see, or that allows us to determine whether or not we would expect there to be a significant difference across the levels of each factor or between the treatment combinations. It also allows us to understand what kind of interaction we would be dealing with if we did find evidence of an interaction from the ANOVA, the two-way ANOVA F test. So we left off working through an example of how to evaluate interaction diagrams. So every interaction diagram can be used to determine if we have evidence of a difference in the main effects and an evidence of interaction. So for example, in interaction diagram 1, we compare the levels of factor A, so the averages of factor A. we can see that the red dashes here are at the same point. That indicates no main effect for factor A. Okay, so that's why we have a no for factor A below. The blue dash lines are at different levels. So the average for B1 is at 40 and the average for B2 is at 30. Those are different values, which indicates a main effect for factor B. Finally, the lines are parallel. This indicates no interaction. In diagram 2, we have the same system of assessment. So the average of A2 is at 40. The average of A1 is at 30. That indicates a main effect for factor A because those values are not equal. So here we have a yes. For B1 and B2, the average is the same value, which is 35. This indicates no main effect for factor B because that value is the same. So we have the no. Finally, we have the two lines sitting on top of each other. So we have a parallel system. That indicates no main effect for the interaction, or rather, sorry, that indicates no interaction because the lines are parallel. In the third diagram, we can see that the average for A2 is higher than the average for A1. So that indicates a main effect for factor A. Then we can see the average for B2 is higher than the average for B1. That indicates a main effect for factor B. And then we can see that these lines are not parallel to each other, but they are not crossing. So this indicates interaction, but we would typically define this as a weak interaction or potentially weak interaction. Okay, now we can do the same things for diagrams 4, 5, and 6. Okay, so in diagram 4, we have the average for A1 and A2, and that's at the same point. So we have no main effect for factor B, for factor A. For factor B, we can see that the averages again are at the same point. Okay, so for B1, the average is 35. For B2, the average is 35. So that means we have no main effect for factor B. But then we can see that these lines cross right in the middle. This would indicate interaction effect and a strong interaction since we have almost perpendicular lines. So that would mean, yes, we have an interaction in the fourth diagram. Okay. In diagram 5, the average of A1 is 35. The average of A2 is also 35. Okay, so we have no main effect for factor A. For factor B, we have an average at, that would be about 32.5, and then an average at 37.5. So those are different values. For B1 is greater than B2 in this case. So that indicates potential main effect for factor B. And then we can see again that these lines are clearly not parallel and they actually intersect at A2. So that would imply interaction. All right, and then in the last system, this would be what we would think of as a dead system or a very boring system, I guess. So we would have, you can see that the red points are both at 32.5. The blue averages are also at 32.5 and the lines are parallel. So this system has no main effect for A, no main effect for B, no interaction. Any questions? Right. I'm not seeing any questions, so I'm just going to keep moving on with the material. But if you guys have any questions at any point, please let me know. Okay, so as a reminder, we use the interaction diagrams, or sorry, as a recap, we use the interaction diagrams to determine if we have evidence of a main effect or an interaction effect. The interaction diagram is simply a plot of the treatment combination means. So the y-axis will always be the value of the response variable, and then the x-axis and the legend can be used for either explanatory value. So you can put explanatory variable b or number 2 on the x-axis, or you can put it in the legend box. It doesn't matter. In either way, regardless of how you code for the explanatory factor, you'll end up with the same solution in terms of the system. When the lines are parallel, this indicates no interaction. When the lines are not parallel, this indicates interaction. Typically, if the lines cross, we would think of it as a stronger interaction. If the lines are not parallel but not crossing, we would think of it as a weaker interaction. Okay, now the question then becomes, from the interaction diagrams, I have evidence that there could be a main effect, and I have evidence that there could be an interaction effect. But is there statistically significant evidence? So that's what leads us into the next part of the lecture set, which is the development of the two-way ANOVA F test. Okay. When we are working in a two-way ANOVA situation, again, we will have two explanatory variables, and we will have what is called replication at each treatment combination. So this diagram shows the layout of data that would typically belong to a two-way ANOVA. Okay, so we have factor A, so this would be explanatory variable 1. We have factor B, this would be explanatory variable 2. You'll notice that factor A we designate as having little a levels. Factor B we designate as having little b levels. The values here inside the table, okay, these are the responses. Okay, so these represent the actual measurement at each treatment combination, and we have little r responses. So this is the number of replications. Okay. So for example, in the illustration at the start of the lecture set, factor A would be golf ball brand, so little a would be 4. Factor B would be golf club type, so little b would be 2. And we had 4 values at each treatment combination, which meant that we had 4 replications, so little r was equal to 4. So we could set up an interaction diagram by just taking the mean at each treatment combination. So we would have a mean for the replications at each of the different combinations in the experiment, and then we can develop a table of means and then build an interaction diagram from that table. With a two-way ANOVA, we are basically saying that our response variables are again the function of some normally distributed random variable. So we again have this epsilon term here. So the epsilon ijk is normally distributed with mean 0 and variance sigma squared. So we are assuming now that every value in the experiment has the same variance. Every single value is normal, but the mean of the distribution to which that value belongs is a function of both the main effect and the interaction effect. Okay, so in general, we're writing x I j k is distributed normal with mean alpha I plus beta j plus alpha beta ij and variance sigma squared. Right? So this basically just means that we now have a number of means that is equal to the total treatment combinations. So for example, if little a equals 2 and little b is equal to 2, right? Then we would have, well, we would have, for example, x 1k is distributed normal, mu plus alpha 1 plus beta 1 plus alpha beta 1 comma sigma squared. Then we would have x 2k is distributed normal, mu plus alpha 1 plus beta 2 plus alpha beta 2 comma sigma squared. So this is actually, and then you'd have the same things for the other values, but this is really not all that different from a one-way ANOVA. In a one-way ANOVA, we're just saying every value has its own mean, but they're all normal and they all have the same variance. In the two-way ANOVA, we're actually saying the exact same thing. We're saying every value has its own mean, but that mean is influenced by the main effects and the interaction effects. But they're all normally distributed values and they all have the same variance. So it's the set of assumptions is pretty much the same for the two-way ANOVA as it was for the one-way ANOVA. We're just considering an extra explanatory variable, which means that we're considering an extra set of effects on the population mean. So the assumptions for the two-way ANOVA procedure will be pretty much the same as they were in the last two illustrations of ANOVA examples that we looked at. In particular, you'll notice we have, the normal population assumption and the constant variance assumption. And both of these can be evaluated using residual analysis. So we can check for normality and for constant variance in the same ways that we had done before. So for example, if we compute the residuals, we can build a normal probability plot of the residuals. If we compute the residuals and we define the residuals by the group they're in, we could then use something like the rule of 2 to compare those values, or we could use Levene's test, or we could compare box plots of the values across the different treatment combinations. All of these options would result in the same, would allow us to check the assumptions of the procedure. We also have our independent samples and SRS sample assumptions, and that's something we would just have to determine based off of the information in the question. Okay, in a two-way ANOVA, we now decompose our sum of squares to take into account the different main effects and the interaction effect. So notice our SST term here. This is the same SST as for one-way ANOVA and CRBD. Okay, so the SST always has the same definition. It's just the total deviation of each observation from the sample mean squared and added together. And this sum of square total term can be broken up into 4 different compartments in this case. So we have SSA, which is the sum of square for explanatory factor A. We have SSB, which is the sum of square for explanatory factor B. We have SSAB, which is the sum of square for the interaction effect. And then we have an error term. Okay, so our ANOVA table is actually going to be comprised of a source for explanatory factor A, a source for explanatory factor B, an interaction source, and then an error source. So there will be 3 different F tests that fall out from the two-way ANOVA table. Okay, so our two-way ANOVA table will look something like what's given on slide 21. And this is going to plug in at the same step of our hypothesis tests as they did in the one-way ANOVA case and the two-way ANOVA case. So on step 3 of the testing procedure, we would just have our two-way ANOVA table. and then we can utilize the information for whichever source we are interested in. So for factor A, for factor B, or for the interaction. Okay. So it follows that the two-way ANOVA analysis or experimental design will lead to 3 different F-tests. An F-test for the interaction, and then an F-test for each main effect. And these F-tests are effectively identical to the F-test that we saw in the one-way ANOVA case or in the CRBD case. In the case of the interaction, we're basically just saying the null hypothesis says that the effect of the interaction on the mean is consistent across all treatment combinations. So basically, we're just saying that the mean at every treatment combination is the same versus the alternative that a difference exists between some set of treatment combinations. On step 2, we have that the means across all levels of factor A are equivalent versus the alternative that a difference exists between some set of means of treatment A means. And then for factor B, we would have the same type of test. So the means across all levels of factor B are equivalent versus the alternative that a difference exists across between some pair of means for treatment B. Right. So this is an extension of the one-way ANOVA case where we now have 2 explanatory factors. But because we have 2 explanatory factors, we also consider interaction between the levels of the explanatory factors. So in our ANOVA table, we now have a test for one explanatory factor, we have a test for the other explanatory factor, and we have a test for the interaction between those explanatory factors. Okay. Now, there's one other test that we can construct from a two-way ANOVA analysis. And that is what is called the model utility test. The model utility test you can think of as a general test of the entire system. So we use the model utility test to determine if there is evidence of a difference in means across the factor levels and the interaction effects kind of in one shot. So typically, when we run a two-way ANOVA, we would start by constructing interaction diagrams. And from the interaction diagrams, we would assess how the system appears to be behaving. Then we would run the model utility test. And if the model utility test gives evidence that the null hypothesis should be rejected, this would mean that there's evidence of some effect in the system. So there is some, in the system, there's a difference in means across either the levels of each treatment or the overall interaction. So it's a global test for treatment effect. So we use the model utility test sort of as a pre-test to determine if we should compute the interaction test and then the main effect tests. So there is, with the two-way ANOVA, a structured pattern to how we would progress through the analysis. That being said, obviously, when you use software to construct two-way ANOVA tables, you'll be able to see where the differences lie. So directly from the p-values, you can see, okay, I have an interaction effect or I have a main effect for one of them or both of the explanatory factors. But we can use this model utility test as a precursor to running those additional tests. Okay, so in a two-way ANOVA analysis, we would start off by running the model utility test. If the model utility test gives evidence of a treatment effect, so if we reject the null hypothesis in the model utility test, then we would run a test of the interactions. And then if the test of interactions rejects the null hypothesis, we would then test the main effects. And then following from those 3 tests, we would then compute the multiple comparisons for the interactions or for the treatment combinations or the main effects, depending on which null hypotheses we reject in that testing procedure. Does anyone have any questions? Okay, so for the golf example that we used at the start of the lecture set, this is the two-way ANOVA table that we can compute from that set of data. So you can see that we have a source for the golf ball brand. So this could be like our factor A. We have a source for the club effect. So this could be factor B. And then we have our interaction. And then the ANOVA table unfolds pretty much the same way as it did in the one-way ANOVA case and in the completely randomized block design case. So we have our degree of freedom for each source. So there were 4 golf ball brands, right? So this is just 4 minus 1. There were 2 club types, so that's 2 minus 1. This is going to be 4 minus 1 times 2 minus 1. This is just going to be little n minus 1, and then the 24 would be the difference between them. We have our sum of square measurements, which would be computed using the formula in the decomposition of the sum of square. We have our mean squares, which are found in the same way they were before. So sum of square divided by degree of freedom. And then we have our F statistics. And in each case, the F statistic is always the MSE for that particular source divided by the MS error. All right, so for this illustration, we're going to start by conducting the model utility test. Then we are going to determine if there's any evidence of an interaction. Then we are going to determine if there's any evidence of a main effect. And then in part D, we're going to give an interpretation of the interaction diagram for this particular experiment. So A, B, and C here, this is our testing procedure. So in parts A, B, and C, we are just breaking down the testing procedure for a two-way ANOVA that was discussed on the previous slide. In part D, we've constructed our table. We constructed a table of means, and then we have plotted each of those means in an interaction diagram. So this would be done the same way that it was in those illustrative examples we saw at the start of the, near the sort of mid part of the lecture set, I suppose. Except that we now have 4 different levels for the golf ball brand. So we have some extra levels on our interaction diagram. But in general, the way that we would interpret the diagram is the same, except that we would start working into components when we're talking about differences in brand type. But we'll come back to talk about that. Okay. So here is the table of means for the golf ball brand experiment. So each of the values that are shown here inside the table, that's computed by taking the average of the 4 values that are given on slide number 3. So these are the averages of the replications at each of the treatment combinations for this particular experiment. Okay. All right, so we're going to start off by working through the model utility test. So let's just assume for now Okay, so we're going to assume assumptions are intact. More on assumptions later. So for now, we're just going to work through examples of the testing procedures, but we'll talk about the assumptions a bit later. Okay, so for the model utility test, we're going to have H0. There's no evidence of a treatment effect. Okay, versus HA, there is evidence of a treatment effect. Okay, and then on step 2, we would declare our significance level. Okay, and then on step 3, we would compute our F statistic. So we're going to have F, and this is going to be SSE or SSA plus SSB plus SSAB divided by MSA plus MSB plus DFA. B divided by MSE. All right, so this is going to be 801 plus 32,893 or 32,093 plus 766 divided by 3 plus 1 plus 3. And this whole thing, actually, I'm just going to move this down. Is going to be divided by the MSE, which was 34. All right, and then I'm just going to check this value because I don't think what I wrote down is quite correct. Okay, so this is going to be 4,808.571 divided by 34, which is 141.4286. Okay, so we can see that for the model utility test, we have a very large F value. So it's not, or we would expect to be rejecting the null hypothesis in this case, because an F value of 141 is certainly going to return a P value close to 0. But we can verify that in the usual way. So on step 4, we can take the critical value approach, or we can take the p-value approach. Okay, so if we take our critical value approach, we're going to have an F statistic on 0.05. The degrees of freedom for this F statistic will be the DF for the model utility test. So that's going to be the sum of the degrees of freedom of A, B, and A plus B. So this is going to be 7. And the degrees of freedom for the error term, which was 24. Okay, so we have to pull out our F table now. Okay, so we're looking for a degree of freedom on 7 and 24. That's probably going to be page 1. It is page 1. Look at that. Oh, no, it's definitely not page 1. 7, nope. Yeah, okay. So our first degree of freedom is 7. Our second degree of freedom is 24. We have 0.05 here. So then we go to our third column, and that's 2.42. So our critical value for this test is 2.42. Okay, and then we can clearly see in this case that the test statistic is very far into the tail here. Okay, and then if we take the p-value approach, all right. So in this case, we're going to consider our test statistic, which is 141.4286. This little green shaded part here is going to be the p-value. So in this example, I'll just move this over to give myself some room. Okay, we're going to have the p-value is equal to the probability that f exceeds 141.4286. If we go to our F table, okay, we're working in this block of numbers here. So you can see that our F value is much larger than the largest listed value, right? So 141 is much larger than 3.99. So we can see here that the p-value is then going to be less than 0.05. So since the probability F exceeds 141.4286 is less than 0.05, then the p-value is less than 0.005. Okay. And then on step 5, we can reject H0 based off of either approach. Yeah, the test statistic is in the rejection region. Yep. And then on step 6, we can conclude at the 5% significance level, the data provide sufficient evidence to suggest that there is a treatment effect. And then now that we have evidence of the treatment effect, we would then move on to test for evidence of an interaction effect. And then if we have evidence of an interaction effect, we would move on to test the main effects. So on Wednesday, we'll start with the interaction test for the two-way ANOVA, and then we'll continue to progress through the testing procedure and move on to multiple comparisons from the two-way ANOVA procedure. Okay, so I'll stop there for today. As always, if you guys have any questions, please let me know. And then just a reminder that we have the midterm is on Monday, quiz 2 is a week from today. Assignment 4 is due March 5th, and lab assignment 3 is due on Monday as well. All right, so I'll talk to you guys on Wednesday.